Our first speaker this afternoon is Daniel Smania from Brazil, and he speaks about Birkhoff sum of distribution.
Thank you very much, Carlos, and thank you very much for the organizers for the invitation. It's really good to be here again in this nice auditorium. So I'm going to talk about Birkhoff sums as distributions. This is a joint work with Clodoaldo Ragazzo, but I'm going to cite results also to Vivian Baladi and Amanda de Lima, who was a PhD student of mine. So, okay. So most of these results can be found in these two, new results can be found in these two preprints, and the old ones you can see the references in these two preprints, okay? So there is this term distributions in the statement, in the title. So let me explain really fast what I mean by that in this context. So distributions is just a linear functional in the space of C-infinite functions. Okay, so you pick C-infinite, pick like a compact manifold, maybe with borders, without borders, and consider all the C-infinite functions from this manifold to R, for instance. And you can consider C-infinite topology in this space. So you can consider linear continuous functionals on this space, and this is a distribution. So that's what I'm going to call a distribution. And this was invented by Lawrence Schwartz a long time ago, and it is really important if you wanted to understand PDEs and harmonic analysis. You cannot do this basically without distributions. So let me give you just a basic examples of distributions. For instance, one case that you're going to appear over and over again in this talk is the space, just pick an interval 0, 1, compact interval, and you can consider C-infinite functions in the space of continuous functions. So if you pick like a Lebesgue integral, we pick a f that's C-infinite, you integrate, this is a measure, every regular measure actually is a distribution in this context, right? So if you pick it like a Borel regular measure in this interval 0, 1, this is going to be a distribution. It's just pick f and integrate this f with respect to the embodied this measure, okay? But there are other examples. So this Dirac measure on the point a half is exactly the same situation. It's a measure, it's a Dirac measure, but there are distributions that are not measures. For instance, the last one that you see here is just pick f and calculate the derivative at some point, let's say 0.1, and then you calculate the third derivative in another point, and add this. This is a linear function in the space of C-infinite functions. Okay, so this is also distributions. What is nice about distributions is that you can put all these different objects, measures, functions, derivatives, all in the same space. Okay, so that makes you'll be able to derivate these things and make a lot of things that you do with functions. You can at least formally do this with distributions and make calculations. This is quite useful. Okay, so but in this constants, how the distributions is going to appear in this talk is a situation where you have decay of correlations, fast decay of correlations. So suppose you have a dynamical system, you have an invariant measure, and pick a square integrable function f. So in this context, you know that if this invariant measure is really strongly mixing, this converges to 0, this expression that you see here, actually. And you can see in many cases, you can give some rate for the convergence of this thing, okay? A especially interesting case is when you have exponential decay of correlations. Exponential decay of correlations, this integral decays at an exponential rate, okay? There's also polynomial decay. Some situations have just polynomial decay of correlations. And if this is fast enough, this is going to be enough to our study, okay? So usually in this kind of, when you wanted to study the decay of correlations, you need some strong assumptions about f that you see here, and some, weak assumptions about f. Let's say f is just integrable or square integrable. And the other function should be much more regular, usually Holder, boundary variation, some sublevels space or something like that. And then under these conditions, if the dynamic is very hyperbolic, expanding, or the Nosov map or something like that, you can have that these integrals converge exponentially fast to 0. Okay, so that's exponential decay correlations. So in this setting, suppose you have a fast decay of correlations like exponential or polynomial with a very fast degree, okay? So in this case, if you pick a C-infinite function, you can associate with C-infinite function G, this linear function in the space of C-infinite functions. You just integrate, add all these integrals up to infinite, and this makes sense because this is summable. So this defines a linear functional in the space of C-infinite functions, okay? So that's the kind of, this, you can see this, you can interpret it this like a Birkhoff sum, right? You pick the Birkhoff sum of F and multiply by G and integrate term by term. Okay? So this is like to think Birkhoff sum has a distribution. So that's the way we're taking here. Okay, all this sounds very artificial. What's the motivation for that? So there are many motivations. I'm going to give one today that I like very much. But one of these reasons that, one of the questions that you can ask about distribution is the regularity of distribution. So we wanted to see, okay, is this a function? Is this a measure? Is this whatever? Okay, so that's the kind of question you want to ask. And especially in one-dimensional dynamics, you can do something a little bit different if you don't like distributions. Suppose this distribution is regular enough that you can calculate embodied variation functions. Then you can integrate this function, this distribution from 0 to x. You just calculate the distribution in the function, the characteristic function of 0x. So this gives you a number. So for every x, you associate a number. So this is like the integral of the distribution. Okay, and ask about the regularity of a distribution is ask something about the regularity of this function alpha. For instance, if the distribution is a C-infinite function, so this alpha is Lipschitz, is if only if. Okay, if the distribution is a Holder function, so alpha is 1 plus Holder, so 1 plus a Holder or something like that. Okay, okay. So what is the motivation for this kind of study of these distributions is the following. There are many kinds of one-dimensional dynamical systems. Here you see a list, that's not an exhaustive list, but there's piecewise expanding maps, unimodal maps, multimodal maps, deformations of the circle, homeomorphisms of the circle with breakpoints or critical points. And there also, that's very hot today, generalized interval exchange transformations. All these kinds of dynamical systems are one-dimensional dynamical systems acting in an interval or either the circle or the interval. Responsible. And especially the last ones, you have some kind of Helmholtzization that I like a lot. I'm not going to talk today, but I like it. But what's very specific in one-dimensional dynamics is the following. Okay, all these maps that I listed there are not actually structurally stable. If you perturb a little bit, you change the topology. For instance, for piecewise unimodal maps, maps which just continuous maps with just one turning point, there's something called a topological entropy of these guys. And if they're expanding, this is a complete topological invariant. Two maps with the same topological entropy are topologically conjugated. And you can perturb the topological entropy. You have some topological entropy. If you perturb your map, you can change the topological entropy, so you can change the topology of the map. But what's interesting is that I think that's quite unique for one-dimensional dynamics is that the topological class of the map quite often is a manifold with finite codimension. So if you pick like all maps of some class, let's say unimodal maps, and pick all maps that are conjugated with a fixed one, some F naught, this is a manifold in this space. The manifold with finite codimension. So this was proven in some of these cases, not all the cases that I listed. And that's one of the motivations. Try to prove this kind of things for many settings in one-dimensional dynamics. So that's interesting because this is like Teichmüller theory. You fix some topology and you pick all the possible geometric realizations of this topology, or this topological dynamics. And you can see how the geometric properties of the map, like Lyapunov exponents, topological entropy of the physical measure changes when you change the representation. This is exactly like Teichmüller theory. Yes. Well, it's a Banach manifold with infinite codimension. Okay. Yes, exactly. So the level curves of the entropy, the topological entropy, are Banach manifolds. Okay, that's not obvious, but it's true. Okay, so that means that it's very rich. It's like, Teichmüller theory of Riemann surfaces. You have many Riemann surfaces with looks like a bitorus, for instance. It's topologically the same that a bitorus, and you can see, you can ask how the length of some homotopic class of some geodesic, the length of a geodesic in this homotopic class changes when you perturb, you move in the Teichmüller space. So you can do exactly the same kind of questions here, okay, for measures, for periodic points, and so on and so forth. Okay, so the first step is to prove that's rigid. So you can really deform these things. They are not rigid, right? Like in the first lecture today. Some dynamical systems are very rigid. That's not the case in most of these dynamics, actually. Okay, so that's the situation that you expect. We expect you have this class of maps, unimodal maps, interval exchange maps, so on and so forth. And inside this class, you can consider the topological classes, and you expect that these topological classes are Banach manifolds, infinite dimension, but finite codimension. Okay, so in this finite codimension world, it's pretty much like a structurally stable map. Okay, you cannot destroy the topology. Okay, so everybody in this topological class has the same dynamics. You can consider smooth curves inside, and you can see, okay, what happens with the periodic points? What happens with the invariant sets? What happens with the House dimension of the invariant sets when you perturb, when you go to a path in this topological class? Okay, so I like this very much. For instance, with Viviane Baladi, you try to understand how the physical measure is perturbed inside the topological class. So this is called a linear response problem, and we like very much this kind of problem. So the long-term goal is not the goal of this talk. I'm going to give some results in some situations, but the long-term goal is to provide a general method to prove, to show that these topological classes are finite codimensional smooth manifolds. And I hope that works for many, many settings. So let me give you some blueprint of the method. I call it this abstract nonsense because you don't need too many assumptions to do these calculations that I'm going to do here. So suppose have a smooth family of dynamical systems. And suppose that there are no bifurcations in this family. So everybody has the same topology, okay? So for every T, there is a conjugacy, AGT conjugated FT and F0, okay? And usually in this setting, I think it's a little different from the setting, again, for the first letter, Daniela, that the centralizer of these things are completely trivial. Usually, most of the time, it's completely trivial. So there's just one conjugacy, actually, between these two guys. So there is, for every T, you have this family of go to T to AGTX. So the thing is, usually, as I told you, these maps are not rigid, usually, not very rigid. But turns out that the conjugacy is not regular. It's not like Lipschitz or absolute continuous or CR or something like this. But with respect to the parameter T, it happens very often that this family is smooth. So the conjugacy is smooth with respect to the parameter T, not with respect to the X in the phase space, but with respect to the parameter T. So this is smooth. So what you can do is differentiate this equation. I'm not going to do the calculations here. Yes. Yes. So T is not the time, T is the parameter. So we have a family of dynamical systems, FT, and F0 and FT are conjugated. So there is a conjugacy HT that conjugates the two. Okay. So there is another variable that is X in the phase space that I'm not showing here. Okay. So it's a family of conjugacies. Okay. So what is nice is that you can differentiate this, is exercise to differentiate this. And when you differentiate, what's really surprising is the following. this family of conjugacies, at least for me, this family of conjugacies satisfies our ordinary differential equation, the same kind of ordinary differential equation that you learn in your first course of ordinary differential equations. And AHT satisfies this initial value problem, this ODE, and alpha T that appears in this equation, right, that defines this equation, satisfies this cohomological equation that you see in the end of this slide. So in this slide, you can see here, this guy, you know the family, and turns out that very often you can solve this equation to find alpha without knowing the conjugacy. So that's the argument. You pick some family, differentiate this family, find the solution for this cohomological equation, you find this alpha T, and then you solve this equation, and this gives you the conjugacy. Okay, so that's the tree. So this cohomological equation is going to appear over and over again, is one of the main things in this talk. So you can do the argument backwards as far as you can integrate this ordinary differential equation, okay? So suppose that for every T, you have a family. You don't know if there is bifurcations or not, if there aren't the same topological class or not. So suppose you have this family FT, and you can solve this equation, find this alpha T that satisfies this cohomological equation. And suppose these solutions are regular enough in such a way that this ordinary differential equation has a unique solution. That is, this is uniquely integrable, okay? If this ordinary differential equation is uniquely integrable, you can easily prove that HT, the solution of this ordinary differential equation, is indeed the conjugacy between FT and F0. So you can reverse the argument. As far you can find regular solutions for the cohomological equation, okay? So you reduce the problem of find the conjugacies to a cohomological equation problem. Find resistance, regularity of the cohomological equation, of solutions for the cohomological equation. Okay, sorry. I think, yeah. So the idea is the following. Suppose you wanted to prove that the topological class is a manifold. So you need to characterize the tangent space at the point F0. So the tangent space is going to be all the vectors that V that has this, there's a solution alpha for this cohomological equation. And this alpha is regular enough to allow the unique integrability of that OD. Okay. So what is nice about it, what is nice about this is that you reduce the problem of find these conjugacies to find this alpha, to find the regularity of alpha. You transform the problem in infinitesimal problem. Instead of looking for conjugacies, you look for infinitesimal conjugacies. Alpha satisfies this equation, is called an infinitesimal conjugacy. Okay, so the motivation for this comes from complex dynamics. Many of you know about this. So there is a very large body of work in complex analysis. There's a method called holomorphic motions that's extremely successful. There's developed by Mayessa and Sullivan in the 80s, and it's extremely successful to deform complex dynamics. So this change, well, it's one of the things that changed completely the field of holomorphic dynamics. And one in particular for quadratic-like maps, that's kind of version of quadratic maps in the complex plane. There is this result of this paper of Lubitsch, that he characterized totally the tangent class of the topological classes of these the tangent space of the topological classes. And there's also a result by Riesler pretty much in the same time, where he understands this is more local, it's closer to the circle perturbations of the real analytic perturbations of circle diffeomorphisms, rotations, sorry, where he also proved that topological classes of real analytic diffeomorphisms satisfy some different condition are also Banach manifolds, okay? But these two methods, these two papers use in a halfway complex dynamics. So you need to go to the complex plane using these complex methods, quasi-conformal maps, holomorphic motions. So these methods are not available usually for finite smoothness maps, dynamics with finite smoothness. That's a big problem. And this is a very besides to be extremely successful, it's something that complex dynamics is extremely successful in the last 40 years. You cannot, unfortunately, no one knows how to apply these methods for things that are not real analytic. Okay. Okay. So another connection that I wanted to do is the following. You can see this this problem about study the regularity of the solutions of this cohomological equation has a problem about partial hyperbolic endomorphisms, a lot of Katok, for instance. So we have this paper of Milner about this example of Katok of pathological foliations. And if you consider a family of piecewise expanding maps in the interval, for instance, and suppose that everybody is topologically conjugated with each other, you can consider this map, capital F, that you see here. And this map is partially hyperbolic. It's a partially hyperbolic endomorphism. It's not one-to-one, but it's a partially hyperbolic endomorphism. And you can see that the horizontal direction is expanding. It's obvious because these maps are expanding maps in the interval. But this direction that if you pick alpha t, that solution of this cohomological equation, this alpha hat is the central direction, gives you the central direction of this endomorphism. So study the regularity of alpha is the same that study the regularity of alpha hat, this gives you the central direction of this partial hyperbolic endomorphism. I'm not going to say too much about this because I don't have any results. Well, I have some results with Clodoaldo about this specific case. I'm more curious about, can you do that for other kinds of partial hyperbolic maps? I don't know. For instance, we know that there's Gabriel cited many results, including results by M. Wilkinson, Avila, and Viana about in some situations defoliations are pathologic, right? In many situations, and there are some. I think Itahazibi has some results about open set where you have this pathological foliations for partial hyperbolis. Sorry, I'm not citing everybody. I don't know all the details, but I wonder if you can prove something about the regularity of the central direction when it moves along, for instance, the stable manifold or unstable manifold. If the central directions move in a very complicated way, as are going to see in this case. In this case, you have some very concrete results about it. Okay. So about this ordinary differential equation, if you do the first course of ordinary differential equations, you know that if alpha t is Lipschitz, then the flow is Lipschitz. That's the first result that you prove in ordinary differential equations, existence and uniqueness in this setting. But usually this alpha t is not going to see. When you have a lot of periodic points are dense, you don't have this alpha t is Lipschitz. It's very unlikely. So it turns out that if alpha is just continuous, that's not enough also, or alpha is just holder, this is not enough to get unique integrability. So what you need usually is some regularity between holder and Lipschitz. And the two that appears quite often in the literature, the first one is log Lipschitz that you see there. And the other one is Zygmunt that appears a lot in complex dynamics. Okay, these two conditions implies unique integrability of the ordinary differential equation. You don't learn this in the first course, but it is true. And actually you can see here, right? So have if alpha is log Lipschitz, then the flow is holder. If alpha is Zygmunt, so the flow is a quasi-symmetric map. If alpha is Lipschitz, then HT is Lipschitz. And actually you can give very precise estimations about the holder continuity and Lipschitz continuity or whatever using this information, okay? These two ones are the most important ones in this talk. Okay, so that's the nice thing. So what the connection of this with the first slides about distributions? So suppose you have a solution for this equation, or this cohomological equation that you see there. And let's pretend that you can differentiate with respect to x. Okay, let's pretend, let's formally derive this. So if you formally derive this expression, you get the second line. That's another cohomological equation for the derivative of alpha. You know what is in the left side. In the left side, you have this ugly observable. But you know, if you know alpha, you know this guy. And you wanted to find, so the derivative of alpha is a solution for another homological equation. This is like classical Levitsky homological equation, okay? And turns out that the formal solution for this homological equation is given by this expression here. So the formal solution is a Birkhoff sum of some observable phi that's given by this ugly expression. Okay, so this last proof that, but in the paper you do all the proper calculations, and actually this is true. So alpha, if there is a solution alpha for this homological equation, the derivative in the sense of distributions of alpha is a Birkhoff sum. Okay, so that's an interesting connection. Okay, so the main problem that I'm going to deal with from now on, my last an hour, is to solve this equation, try to see when I can solve this equation. So you can actually forget everything I said until now, and that's the dynamical problem. I have a dynamical systems, F naught, I have some vector V, and I wanted to find solutions of this equation to study regularity. That's what I wanted to do. Okay, so there is this little toy model in Amanda de Lima thesis. That's not, by the way, the main result in the in her PhD thesis. There's something that's much more complicated. This is kind of a toy model for the main result. So suppose you have F expanding map on the circle that's regular enough, and suppose that V is also regular enough. So is exercise to prove that alpha, there is a continuous bounded solution, actually continuous solution for this homological equation that you see here, for every V and every F that's expanding, okay? But turns out that Amanda de Lima proved that regularity of alpha is connected with the ergodic theory of this dynamical system. So the theorem is kind of technical, so I'm going to clean a little bit, lie a little bit, and I'm going to put here the expression. So suppose you wanted to prove that alpha is regular. If you wanted to prove that alpha is Lipschitz, you wanted to prove that the left side is bounded. That's what you prove, right? But in the right side, what you see is something related with ergodic theory, is a Birkhoff sum of the observable phi plus a error that you can ignore, okay? So this result is a connection between the regularity of alpha. This is the infinitesimal conjugacy, is a problem about find conjugacies between maps, and ergodic theory. So that was very surprising for me, that there is a relation between these two problems. You can use ergodic theory to understand the regularity of alpha. That was very surprising for me. And that's one of my favorite things in this talk. So there are going to be 3 hertz along the talk. That's the first one. And that's one of my favorites. The connection between regularity of alpha and Birkhoff sums and ergodic theory. So I'm not going to explain what is N. You can explain later. Someone wanted to know. So a consequence of this is very one-line consequence, is that in this setting, expanding maps of S1, the solution alpha is always a Zygmund function. And in particular, you have unique integrability, okay? And in particular, the conjugacies are quasi-symmetric. What probably was already known, but is a new way to see this. Okay, another thing is that there is a dichotomy. So that's similar to some results of Amy, Viana, and Avila about dichotomy of regularity of the foliations. So we have the following. Either the solution is wonderful, so wonderful as possible, is C1 plus beta, or is nowhere differentiable. So there is no intermediate step. Either is wonderful, so wonderful as possible, or is nowhere differentiable, exactly like Weierstrass functions. So actually, I can be more precise about that. You can actually characterize when is nowhere differentiable. So alpha is nowhere differentiable if there is one periodic point, just one periodic point, where the sum along this periodic point is different of 0. Okay, so that's basically saying that phi is not homologous to a constant. So if phi is not homologous to a constant, then alpha is nowhere differentiable. We just need to find one point where this holds. Okay, there are another equivalence. I'm not going to tell you about this today. So let me give you an example that's connected with LaDebré talk. So we have these Weierstrass functions that he talked about it. So that's the example of the Weierstrass function, but it's a very special situation where A, B is equal. So you have the coefficient here. Oops, sorry. The coefficient here is 2 and here is 2. Is a power of 2 here and a power of 2 here. You have the same. So that's like the critical situation. If the number here in the quotient is bigger, like say 3 than 2 there, you have a C1 function. It's wonderful. If the number inside the scene is bigger, then you have nowhere differential. You have that's not sigma. But precisely with this, when 2 and 2 or 3 and 3 or so on and so forth, you have that this function is sigma. Okay. And turns out that you can prove with one line using the previous result that this function is nowhere differentiable. So that's one of the first functions that we know that's continuous and nowhere differentiable. And note that 0 is a fixed point of this dynamical system. And when you calculate phi in this setting, so phi is very easy in this setting because the second derivative is 0 of f is 0, you can see that this is different of 0. So automatically, this implies that this function is nowhere differentiable. So this classical example that has 150 years, probably more, can be seen as this result about the no differentiability of this can be seen as a dynamical result. Okay, I like this a lot. Okay, another thing that you can be more precise about it. So that's a thing that I'm also curious in the partial hyperbolic case. In many situations, you have deformation is pathological. You have this atomic disintegration of the measure. But can you say more about that? So here, okay, alpha is nowhere differentiable, but you can actually give some quantitative information about the regularity of alpha. And it's related with the central limit theorem. So the modulus of continuity of alpha is satisfy some central limit theorem. So what you see here, if alpha is Lipschitz, if you pick alpha x plus delta minus alpha and divide by delta, this is bounded, right? So if alpha is Lipschitz, this goes to 0 when delta goes to 0. It's very easy to see. So this cannot be satisfied, definitely. And turns out that alpha satisfies this kind of central limit theorem. And one, maybe you don't like central limit theorem, but one of the consequences of that is that this function is not Lipschitz in any set of positive Lebesgue measures. Okay, so it's really bad, really sucks. You cannot, it's not just there is some boring exceptional points that you can take off and have a Lipschitz function. You cannot, you need to take almost everything to get a Lipschitz function. So that's really surprising for me too. Okay, so there are some, as I said, there are some previous results for Lyubich. There's some previous results for piecewise expanding maps with Balaji and myself, and also some results for collecting maps that I'm not going to talk today. But there's this new result with Clodoaldo Ragazzo that again is a little technical, so I'm going to give like the clean version of this. So suppose you have a piecewise expanding map, then in the you have a solution. Suppose you have a solution for this cohomological equation V equals to alpha composite to F minus dF alpha. So this solution, in the sense of distributions, we prove that in the sense of distribution, the derivative of this alpha is the Birkhoff sum of some observable. That's this observable that you see here, okay? And a consequence of this, so there's an immediate consequence. It's really easy to prove this using this statement. Again, the regularity of alpha is related with the ergodic theory, okay? So I need to put a hair here because that's again the main thing in this talk. So oops, sorry. You should not have. Yeah. So a consequence of this is that to study regularity over infinite deformations is equivalent to study integrals of a Birkhoff sum. So for every Birkhoff sum, you can integrate to 0 to x, and you get a function. And these two objects, infinitesimal deformations and integrations, primitive of Birkhoff sums, are exactly the same thing. So that's really surprising for me. That's the last part. Okay. Okay. So a consequence of this is the following: if you have that alpha, since alpha is the Birkhoff sum, the derivative of alpha is a Birkhoff sum of some observable, you can use a lot of techniques to study Birkhoff sums, like Perron-Frobenius operators, transfer operators, Lazotte-York inequalities, and things like that. That is very well established in this setting, and prove that alpha is log Lipschitz in this setting. So in this setting of piecewise expanding maps, if you have a continuous solution, then you have actually a log Lipschitz solution. The solution is log Lipschitz. Okay. And a corollary of all these results is this characterization of the topological classes in the piecewise expanding case. So suppose you have a piecewise expanding case, and in this situation, you have some discontinuities, right? So suppose you have a discontinuity like this, here, and here, like this. So in this case, you have how many discontinuities? You have one discontinuity here, one here. Because this has a discontinuity, 2, 3, and okay. So we have 4 discontinuities. So this theorem says that the topological class is a Banach manifold, is multi-Banach manifold, and the codimension of this manifold is 2n minus 2, where n is the number of discontinuities of this point. You should think like this: for every discontinuity, you have 1 degree of liberty for the dynamics here, and 1 degree of liberty for dynamics here, and 1 degree for each side that you see here. So we have 2n minus 2. And moreover, the tangent space of the topological class of F0 is exactly all the V's that has a continuous solution for this cohomological equation. So in this piecewise expanding case, we have a complete description of the topological classes. And I like this very much. Okay. Okay, I'm going to skip here. Yeah. So there is this mysterious observable that probably you don't like that much. It looks very ugly, right? So this phi, what this phi is? So this phi describes the geometry of the map. So suppose you have like a orbit of some point x. So when you deform your dynamical systems, you have an analytical duration of this map. You have HTX that has the same dynamics to FT as X has to F0. Okay, they have this exactly the same. The orbit of X for F0 and the orbit of HTX for FT is exactly the same in the topological sense. But geometrically, it can be different. The Lyapunov exponential of this orbit can be completely different if you deform your dynamical system. So if you differentiate the Lyapunov exponent along this orbit, you can see that you get exactly the Birkhoff sum of phi. Okay. So what this phi is telling you is about how the geometry of the map, how the periodic points, the Lyapunov exponents of the periodic points, the Lyapunov exponents of measures are changing when you deform this dynamical system. Okay, so what's the next steps? So there are many steps you can take. For instance, you can consider no expanding maps for maps with critical points. So there is a class of maps that are not uniformly hyperbolic, but they're pretty close to be uniformly hyperbolic, like Cole-Ekman maps. Okay, so there are a lot of people here that have many contributions in this the Cole-Ekman maps, where you have a positive Lyapunov exponent in the critical orbit. So you can ask if you can have similar results for Cole-Ekman maps, for instance. If you lower the degree of hyperbolicity of expansion, then things get more difficult. For instance, let's say Feigenbaum maps, that maps with the physical measure has 0 entropy, so that's much more complicated. But in the Cole-Ekman case, maybe we can have some pretty soon some nice theories about this. I believe that the main gradient is going to be again ergodic theory, and like using towers or induced maps to study this, to reduce these problems to problems about piecewise expanded maps. Okay, so that's a technique in ergodic theory that you can take advantage in this setting. Okay. And actually, we have some preliminary results with Baladi. Actually, it's quite old by now. It's like almost more than 10 years old, where we study Colorecma maps, such some kind of maps like topological slow recurrence condition that implies Colorecma and also Benez-Carlos condition. So in this situation, we prove that under some codimension 1 condition for unimodal maps, this solution has a continuous solution for every smooth V in this codimension 1 subspace. And the proof uses what's called Baladi-Viana towers. And we believe that it can be used in another settings. This is not so satisfactory because we prove that that's alpha just continuous. We don't know even if it's holder. So I believe that's holder, but or maybe log Lipsch is likely, but I have no idea how to prove this today. Okay. Okay, I think my time is pretty. How much time do I have? 5 minutes. Okay. So I finished. So thank you very much for your attention.
Okay, are there some questions or comments?
Yes. So for like structurally stable, like a Nosov map, certainly you can, but there are a lot of open questions about regularity of alpha T. So I believe that in the, let's say, two-dimensional Nosov diffuse, it's like that solution alpha is sigma, but I don't know how to prove it. So, but notice that it's unlikely that in higher dimension, the topological classes has this nice structure, okay? But probably like the Lorentz flows, for instance, is probably a situation that's very close to one-dimensional situation that maybe you can use something like this. Yeah.
Another question or comment? Okay, if not, we thank Daniel
Thank you very
again.
much.
And we back at 4.